All right, so today we're diving into one of the biggest scientific detective stories ever told. For the longest time, everyone thought atoms were these tiny, unbreakable little balls, the absolute smallest thing you could get. But what if they weren't? What if there was a whole hidden universe tucked away inside? Well, that's what we're going to find out. Let's follow the clues and solve this thing. And it all starts with this one single question. See, John Dalton's theory was beautiful and simple. Atoms are just solid, indestructible little spheres. But as science moved forward, people started noticing little cracks in that perfect picture. It was a puzzle that, once solved, was going to change absolutely everything. So, here's our game plan. First, we'll look at the very first hints that atoms weren't so indivisible after all. Then we'll check out the early sketches of what an atom might look like. Some were close, some not so much. After that, we'll refine the picture with some new discoveries, figure out the rules for how electrons get organized, and finally, we'll crack the code that makes every single atom unique. Okay, our investigation starts right here. That whole idea of a solid, unbreakable atom, it was about to get completely turned on its head by something you've probably played around with yourself. Yep, you heard that right. Static electricity. You know how when you run a comb through dry hair, you can suddenly pick up little bits of paper? How does that even work if atoms are just neutral little marbles? That simple everyday thing suggested a pretty wild idea. Maybe, just maybe, atoms have even smaller parts inside them that have an electric charge. And sure enough, it wasn't long before our first suspects were found. First up, J.J. Thomson discovered the electron, this tiny, tiny particle with a negative charge. Then, building on some earlier work, scientists identified the proton, a much heavier particle but with a positive charge. And just like that, the case was blown wide open. Atoms had parts. So think about it. Scientists now had the ingredients, protons and electrons. But the big question was, how were they arranged? What does an atom actually, look like inside? This led to the very first attempts to draw a blueprint for the atom. J.J. Thomson, the guy who found the electron, he took the first crack at it. He came up with what we now call the plum pudding model. He basically pictured the atom as this big, fuzzy ball of positive charge, and then the little negative electrons were just kind of stuck in there like plums in a pudding. Now, if plum pudding sounds a little old-fashioned, think of a watermelon instead. The big red fruity part is the positive charge, all spread out, and the little black seeds scattered around are the electrons. It was a really clever model for its time. It explained why atoms are neutral, the positive and negative stuff just canceled each other out. It was a solid first guess. But here's the thing about science. You have to test your ideas. And Thomson's model made a really specific prediction. It said if you were to shoot something through this pudding, it should just zip right through with maybe a tiny nudge. Well, another scientist, a guy named Ernest Rutherford, was about to put that idea to the test. And what he found would change everything. So Rutherford set up this amazing experiment. He basically took these tiny, heavy, super fast particles, they're called alpha particles, and fired them like little cannonballs at a sheet of gold foil that was unbelievably thin. We're talking just a few thousand atoms thick. Now, if the plum pudding model was right, shooting these things at the foil would be like firing a cannonball through a cloud of fog. They should just go straight through, right? But that is not what happened. I mean, yeah, most of the particles did go straight through, just like he thought, and a few were deflected a little bit, and this was the absolute shocker, a tiny, tiny fraction, about 1 in 12,000, didn't just get deflected. They hit something and bounced almost straight back. Rutherford himself said it best. He said it was as unbelievable as if you fired a huge artillery shell at a piece of tissue paper and it came back and hit you. It was completely impossible if the plum pudding model was correct. Something was seriously wrong with how they thought atoms were built. So, to explain this, Rutherford just tossed the old model in the trash. He came up with a radical new idea. He said all the positive charge and almost all the atom's weight had to be crammed into a super tiny, super dense center, which he called the nucleus. And the electrons? They were orbiting way out from the nucleus, meaning most of the atom was actually just empty space. This explained his results perfectly. Most particles flew through the empty parts, but the very few that scored a direct hit on that tiny nucleus got knocked straight back. Rutherford's nuclear model was a massive leap forward, a huge win for science. But you know how it is in a good detective story? You solve one mystery and it just uncovers another one? His model had a pretty major problem. So here's the fatal flaw.
The physics at the time said that an electron orbiting a nucleus should be constantly giving off energy. And if it's losing energy, its orbit should get smaller and smaller until it spirals right into the nucleus, and poof, the whole atom would collapse in a split second. But obviously, atoms don't do that. So what was missing? The answer came from a physicist named Niels Bohr. He made a really bold suggestion. He said, what if electrons aren't allowed to orbit just anywhere they want? What if they can only exist in very specific, stable orbits? Let's call them energy shells. And he proposed that as long as an electron stays in one of these special shells, it just doesn't lose energy. It was a bit of a weird idea, but it fixed the stability problem perfectly. And while all this was going on, the final piece of the atomic puzzle was finally found. In 1932, James Chadwick discovered a third particle hiding out in the nucleus. This one had about the same mass as a proton, but it had no electrical charge at all. It was neutral, so they called it the neutron. And with that, our team was complete: protons, neutrons, and electrons. Okay, so we've got the full structure now, but how does that structure actually determine how an atom acts? Well, it all comes down to the electrons and how they fill up those energy shells that Bohr talked about. Honestly, this is the key to understanding all of chemistry. And it turns out there are rules to this, known as the Bohr-Bury rules. First, each shell can only hold a specific number of electrons, calculated by the formula 2n squared. Second, the outermost shell is happy and stable when it has a maximum of 8 electrons. And third, you can't just stick electrons anywhere. You have to fill up the inner shells completely before you start putting any in the outer ones. And this leads us to one of the most critical ideas in all of science: valency. See, all atoms want to have a full outer shell. That's when they're most stable. Valency is just a way of counting how many electrons an atom needs to gain, lose, or share with another atom to get that full outer shell. This one concept is what explains how atoms link up to make everything in the world around us. All right, let's wrap this up. For our final section, we're going to see how these particles we've discovered give every single element its own unique ID card. It really is all in the numbers. There are 2 numbers you gotta know. The first is the atomic number, which we call Z. It's just the number of protons. This is the big one. This number defines the element. If it has 6 protons, it's carbon. Always, no exceptions. The other number is the mass number, or A. That's just the total number of protons plus the neutrons all added together. Now, this setup allows for some pretty interesting variations. You've probably heard of isotopes, right? Isotopes are just different versions of the same element that have a different number of neutrons. Like all carbon atoms have 6 protons, but some have 6 neutrons and some have 8. They're both still carbon, just different weights. Isobars are a little different. They're atoms of completely different elements that just happen to have the same total mass number. And that brings us to our final thought. So if isotopes are chemically the same, they act the same in reactions, but they have these tiny little differences in weight, what could you do with that? Well, it turns out that tiny difference is the secret behind everything from figuring out how old ancient fossils are, to creating medical scans that can see inside your body, to generating clean energy. Solving the mystery of the atom didn't just give us an answer, it gave us a whole new world of technology.